speaker after that is Lawrie, and he's going to tell us about agency and emergent n equals 4 from n equals 1.
Okay, wonderful. Thank you to the organizers for this nice invitation. So great to come back to Philadelphia. I'm very much looking forward to trying to get some of the regional realities that the organizers made available on the webpage. Very well. And today, I can tell you something interesting about classes of superconformal theories. They're very so they're probably based on sort of sequence of work. It's like a paper operator here. Game one, and this is obviously hard to watch for 30 minutes. So I will principally talk about these.
Oh, I didn't turn it on. Thank you. Thank you. So there's a big picture motivation here, which I'll just go through very briefly just to set the stage. So we might be interested in understanding some aspects of quantum field theory. It's a very useful and ubiquitous framework throughout physics, not just high energy theory. And so understanding questions about QFT is great. But generally, outside of some notion of a perturbative regime, it's hard to study these things. So one thing that we know how to do very well is that you take a hard problem, you add some symmetries, the symmetries make the problem easier, and you can compute something. So let's add some supersymmetry. A very confusing pointer. So you add some supersymmetry, and then there are a bunch of quantities which are protected from quantum corrections. I could also say, well, I can think of every quantum field theory as lying somewhere on the renormalization group flow between two conformal field theories. So if I want to start understanding the space of quantum field theories, a good place to start is the space of conformal field theories. So I put them both together and we study the space of superconformal field theories. And since this is the topic of this conference, we might say, what can you understand about this space of theories from some stringy or geometric approaches? And the answer is a lot. So in this talk, I will restrict myself to talking about 4 dimensions. And let's start with thinking about 2 of the most supersymmetric kinds of theories in 4 dimensions. So n equals 4, maximally symmetric, n equals 2. There is an n equals 3 in the middle, but I'm not going to talk about it, so I didn't write it. And these things have a vast a set of tools involving some notions of sort of geometric structures. So you can think about engineering them in string theory through some geometries, or you can think about how the supersymmetry enforces that the koan branch has some kind of complex geometry, and then you can study those kinds of complex geometries and so on. So by now there is a huge set of literature on this, so I refer you just to sort of 2 recent reviews. One by Alessandro and friends, who's here, and one by Jonathan and friends, who's of course also here. But what about n equals 1? So there are a variety of sort of geometric approaches to n equals 1, various different classes of n equals 1 theories and so on. But this is sort of the question that I want to pin as the main motivation behind this talk. So there are a bunch of n equals 1 SCFTs. I think of this as a good proxy for studying quantum field theory. And can I use some of the geometric tools that I'm familiar with more supersymmetry to understand something about this landscape? So let me tell you first something from the bottom up rather than from the top down. So if I just have a 4-dimensional superconformal field theory or conformal field theory, then I can put that theory on a curved background. The conformal symmetry becomes anomalous. It becomes anomalous in a very specific way. There are 2 numbers parametrizing the way in which that becomes anomalous. So a very broad brush sort of, big picture kind of thing, I can think of the space of 4D SCFTs as being parameterized by the values of these 2 real numbers. So these things are called the central charges, and you can think of them as conventional invariants of the CFT. It's just another way of saying that you can think of them as parameterizing the space. And there will be 2 other talks in this workshop by my collaborators, Monica and Jacques, who will talk about some work that we thought about this concept of conventional invariance. So I encourage you to enjoy those talks as well. Okay. And it's not just that you have this sort of space of 2 integers, but you have some structure to it. So there's the A theorem, and the A theorem tells you that if you start with one theory with some particular central charges, and there exists an RG flow to some other theory with some particular central charges, then A monotonically decreases along this slope. So you have this space, and you have some structure to the theories that live in this space. Okay. So we want to understand some subsector of this n=1 landscape, and we want to take advantage of the geometric constructions that we thought about in n=2. So what can we do? Well, here's a really obvious approach. I can take an n=2 theory. It has some flavor symmetry G, and I can say, well, I gauge this flavor symmetry with an n=1 vector multiplet. That's, of course, an n=1 theory. It's a very soft n=1 theory because it's very close to n=2. But that's hopefully what's going to enable us to use some nice techniques. Okay. So today I'll focus on something which I mentioned just earlier, which is the class S construction for 4D n=2. And then we'll play this game. So let me quickly tell you what the class S construction is. So I don't have a clock in front of me, so I will just trust someone to yell at me if I go over. So the class S construction is best represented by this nice picture here. So you start with the 6-dimensional 2,0 superconformal field theory. These are associated to a simply laced Lie algebra, basically because they come from type 2B string theory on an orbifold, so nice geometric engineering. So that's a 6D theory with 16 supercharges. You perform a twisted compactification on an n-punctured genus G Riemann surface. That takes you down to some 4D n=2. And you have to specify some information. So each of these n punctures carries some information, some kind of asymptotic boundary conditions for the field. So you have to provide this data as well. But if you put these three pieces of data together, what these authors tell you here is that you generate a 4D n=2 superconformal field theory. And one of the sort of main attractions of this is that a whole bunch of complicated physical features, like strongly coupled non-perturbative features like S dualities, relating things at different values of the coupling, well, these things are captured in terms of this little bit of geometry here. So you take a hard physical question and you map it into a question about the geometry of a Riemann surface. So that's nice. So now we want to think about these things as building blocks for n=1 SCFTs. So we're actually going to consider two classes of very specific 4D n=2 theories to start with. The first one, they go under the name of DPG. So these are theories that have fractional, I mean, this is for those who know, they have fractional Coulomb branch scaling dimensions, so they're called Argyres Douglas type. And they have been much studied. And they have class S descriptions, of course, which is why I introduced this. So they appear as these two punctured spheres. They have one regular maximal puncture and one irregular puncture. And from this information that is drawn here, you can extract a whole bunch of physical features of the theory. The second class of theories that I want to consider are called GG conformal matter. And these are basically a generalization of a bifundamental hypermultiplet. Imagine you have two SO groups and you want to construct some notion of a bifundamental hypermultiplet. The consistent thing to do is actually have an interacting SCFT there. These things also have a class S construction. There are now 3 punctured spheres with now 2 regular maximal punctures and 1 puncture which is called the subregular puncture. And as an interesting note in nomenclature, the regular that appears in subregular has absolutely nothing to do with the regular that appears here. So these things were sort of explored in great detail in this sequence of papers. So can we start with these 4D SCFTs as building blocks and build some new things? And the problem will just be as follows. Take those theories and consider n=2, or more interestingly, n=1 gauging of all of these flavor symmetries. So actually for n=2 gauging of these types of theories, there is an ADE classification, which we worked out in 2020 in this paper with Monica and Jaewon. But today, that's all I'm going to say about that, and I'll focus on the n=1 classification problem. So here's a simple statement. You can just give this to someone and tell them to go and do the computation. How can we gauge together all G flavor symmetries of a bunch of DPG such that the result flows in the infrared to an n=1 SCFT? And we answered this question in this paper. And the answers look like this. So we started with the cases without conformal matter. So you have a bunch of these theories, and you have an n=1 gauge node. If you want the gauge coupling to be asymptotically free, you look at the one-word beta function, and you see that the condition for asymptotic freeness translates into this condition on the p's. These p's are integers greater than 2, and so you can just enumerate all possible solutions to this inequality. And in fact, they look like this. Kind of ugly, but it's exhaustive. Okay. But that's not quite good enough. Just because I tell you that I can gauge a bunch of n equals 2 SCFTs together in such a way that the gauge coupling is asymptotically free does not tell you that you end up with an interacting infrared SCFT when you actually do this flow. So first, you should determine the superconformal R symmetry following the procedure of amaximization. And then when you flow, you should check that there's no operators that cross the unitarity bound to decouple from the theory as you do this process. And one can do this, and I pressed it early. And the only difference to the table that I previously presented is that this one, this combination of things here, flows to something which is bad in a certain sense. And this thing here requires that at least one of these two things be greater than 2 to get an interacting infrared SCFT. So you see this is very restricted. For example, how would you have guessed that you can only have at most 5 such theories gauged together? Okay, so here's another surprising fact. If the dual Coxeter number of the gauge group, which is n for SUN, and all of the PIs which you've gauged together, if the GCD of those things is 1, then the theory that you flow to in the IR has the same central charges. You see, this happens all over the place. We can just take an example here. If I take here with gauge group SU7, then because then all the GCDs are 1, then this thing flows to something with A equals C. And what's so special about that? Well, A equals C you usually think of as a feature of theories with n equals 3 or n equals 4 supersymmetry. So we want to know if we can sort of understand why this happens and if there's some connection to these theories with higher supersymmetry. In fact, you can do a little bit better. So I said I wanted to consider just a bunch of these n equals 2 theories, gauge them together. What I can actually do is I can gauge them together and also add a bunch of adjoint chiral multiplets. And that equally satisfies everything I said on the previous page. It's a theory which flows in the infrared to an interacting SCFT. And when the GCD condition is satisfied, we have this equals. And there are very few options here. So the reason I'm not focusing on the n equals 2 case here is because the n equals 1 case kind of incorporates that quite straightforwardly, because you can have these adjoint chirals, or you can have 2 additional adjoint chirals, and then there are this very restricted set of options. And of course, you could raise your hand at this point and say, aha, what about 3 adjoint chirals? Well, of course, you can have 3 adjoint chirals together with no copies of this strongly coupled SCFT, and this is just n equals 4 superioris, which you think of in n equals 1 language as just a vector and 3 adjoint chiral. Okay. So let's try and maybe understand sort of where this point comes from, or maybe what the connection is to theories with higher supersymmetry. So first I have to tell you a little bit more about this space. So at the start, I told you there was a space spanned by these numbers A and C. Now I need to tell you a little bit more about the constraints that we know on that space. So for example, in this nice paper from some time ago by Hoffman and Malvasena, they found that if you just take a CFT in 4 dimensions with no supersymmetry, just impose unitarity, then you see that the ratio of the central charges is bounded in this way. And it's bounded below by the value of a free scalar field and above by a free vector. And of course, if you add supersymmetry, as always happens when you add symmetries, things become much better, the bounds become much stronger. And you get this kind of result here. So you see n equals 1, bounds are saturated by free chiral free vector, n equals 2, free hyper free vector, and n equals 3 and 4 are so constrained that supersymmetry itself forces that the central charges are. Okay, so now we've cut down the space somewhat just by imposing this result, and we seem to be lying in some interesting area. So let me tell you one reason why I think having say an n equals 1 theory with identical central charges is interesting. So imagine that such a theory has a holographic dual, something of the form ADS5 times. Then there are some central charges, and those central charges typically grow like n squared, if I say some SUN or something. And the subleadic terms, well, we know how to compute them, or at least we know how to compute them in principle. First of all, there are a bunch of terms at order n, which come from open string contributions. So if you have branes in the holographic dual setup. And there are a bunch of closed string contributions, which typically contribute at order 1. Now, if you want to write down a supergravity dual where AC is exact, all n, finite n, then these two things must somehow conspire to cancel off their contributions. There's one case where we know this happens, that's n equals 4 super Mills. And there it happens sort of in a very interesting way. Tell me when I started. Okay, perfect. Thank you. Yes, for n equals 4, rho is 0. And the contributions from all of these things cancel off order by order in the KK expansion. Exactly. Okay. So quantity also happens to control a bunch of interesting sort of quantities. So there's the Carty limit of the superconformal index. It appears in this entropy, viscosity, and ratio bound. The coefficient of a mixed current gravitational anomaly. It's this single trace higher spin gap. So this seems like a rather interesting quantity that controls some interesting features of conformal fluidity. So now this was sort of a fairly lightning overview, just to say, you can take these n equals 2 constructions, you can construct a bunch of true n equals 1 theories, so they really have n equals 1 supersymmetry, but exactly A equals C. So they behave in some way like n equals 4 super Mills, and let me say a little bit more about how they behave like n equals 4 super Mills. So if you compute something like, so now in this section, I'll focus on the n equals 2 gauging instead of the n equals 1, but we'll get there. So the Schur index of the gauge theory is basically a rescaling of the n equals 4 Schur index. There exists a gradient vector space isomorphism between the VOAs of the n equals 2 and n equals 4 theories. And in fact, in this nice result here, the Nekrasov partition function of the n equals 2 gaugings has the same structure as an n equals 4. So there seems to be some kind of deep thing going on with this connection. And we would like to understand this in some way. So can we push this connection to n equals 4 a little bit further? Okay, so now I'm going to talk about this paper that we had a couple of weeks ago. Take this theory here. This is one of the theories that I've just described. You take 3 copies of d2su2n plus 1, you do an n equals 1 gauging. And you can see that this flows to an infrared SCFT with identical central charges because the GCD between P, which is 2, and the dual Coxeter number, which is 2n plus 1, is 1. But let's actually do a little better and let's work out the central charges. So, okay, gauging breaks the R symmetry of each of these factors. So you, principle, have 3 U1 flavors. One's anomalous. And these things can mix with the UV R symmetry to form the infrared R symmetry, which is given sort of by this linear combination of generators. And these coefficients are fixed by a maximization following intraligator. And it seems either I messed up or my slides are slightly too large. Okay, so a maximization simply says you should write down A, which is given by supersymmetry in terms of the Toft anomalies of the R symmetry. And now I just expand this R in terms of these quantities here, and I end up with this expression for my trial A, and I have to maximize this with respect to the epsilons. And if I do this, I find epsilon is minus 1/3. Okay, so that means that when I flow into the infrared, the superconformal R symmetry is this mixture with this being minus 1/3. And if I do this, I can compute the central charges. If you like, just plug this back in here. And I get this result here. Does this look familiar? Should look familiar. I kind of already told you the answer here. So these are just the conformal anomalies of n equals 4 super Mills with gauge group SU2n plus 1. And just recall, these are conventional invariants. So if I have 2 theories, not what I wanted to do. If I have 2 theories which have the same conformal anomalies, it's consistent with them being the same theory. Doesn't demand they're the same theory, but it's consistent with them being the same theory. But this is interesting. So let's try and look at it a little bit further. Let's try and look at, say, the chiral operator spectrum of these theories. And what we see is that the Casimir operators of n equals 4 Superang-Mills, they have the same charges under all the symmetries as the Coulomb branch operators of each D2G factor plus their super descendants. So an n equals 2 multiplet contains two n equals 1 scalars. You need both of them to construct all the Casimirs. And the single trace operators of n equals 4 have exactly the same charges under the symmetries as the traces of the moment map operators in the D2G theories. These are the only gauge invariant combinations that survive the gauging, of course. And so you can see that the dimension of the conformal manifold is 3, which is the same as n equals 4 Superang-Mills. Okay, so this is sort of interesting. This kind of tells us that, in some sense, these two theories are dual. But can we verify this in a little bit stronger? We've only checked sort of a very limited subsector of the theory so far. So one other thing we can do is we can compute the superconformal index. So the superconformal index you should think of as counting certain short multiplets in the spectrum. So it's seeing a somewhat large part of the spectrum of the theory. And it has some formal definition, which I will not go into, but it's something that, given a theory, compute. So if I look at the D2SU3 theory, it has an n equals 1 Lagrangian description. Yes, and the superconformal index can be determined from that n equals 1 Lagrangian description. And that means the superconformal index of certain gaugings of D2SU3 can also be determined. So that's very pretty. So you get some large horrible expression, which actually we worked out in this paper last year. And if you stare at this hard enough, this is just the superconformal index of n equals 4 with gauge group SU3. Note once again, this SU3 is this SU3, but these SU3s are the SU3R symmetry from the n equals 1 perspective. So you have to look at this a little carefully, but so you should think of this as sort of quite a refined comparison of the short operator spectrum of the two theories. Okay. But maybe we'd like to go beyond SU3, perhaps. But you get a bit unlucky because if you take these D2SU2n plus 1 theories, we don't know of any Mario-Chisson flow, which means there's no n equals 1 Lagrangian, which flows upon deformation to these theories here. So how do we test this duality beyond the SU3 case? Yes. This is a fantastic question that I would like to understand better. We certainly have not looked at anything beyond, like, I wouldn't even say we've looked at the full local operator spectrum, right? We're looking at protected subsectors of the local operator spectrum. So they have the same center symmetry. So n equals 4 Superang-Mills is the center, which is just the center of G. And this theory, I won't go back to it, but the G gauge node in the center of the diagram also has a center which you could quotient by. It also has a discrete symmetry which permutes the lags, which, okay, so there are things one can play with, but the symmetries, even the like one form symmetries, I would say match. Yes, good, thank you. Yeah. So even though we don't know the superconformal index of this theory, we know the Schur limit of the superconformal index out by these authors here, and it's just the expression. This expression is very nice, very simple, much simpler than the one you saw on the previous page. And it's also known that if you have an n equals 1 deformed n equals 2 theory, then there's some limit of the superconformal index which reproduces the Schur index. So now I can just play a game. I can say I take the formal expression for the superconformal index of the gaugings of these guys. I take this particular limit, which on the building blocks, which are these guys, reproduces the Schur index, which is this thing here. And then I will compare that result to n equals 4 Superang-Mills. So the index of n equals 4 Superang-Mills just comes from taking the index of a vector, the index of 3 chirals, and integrating them. So all we actually need to compare is the index of a single adjoint valued chiral multiplet. And in the Schur limit, that's this limit here, the index of an adjoint valued chiral multiplet looks like this. But hey, these two things are the same. So if I take an index, which is a vector multiplet and 3 copies of this, then it's the same as taking a vector multiplet and 3 copies of this. So actually, at least what we can say is that the Schur limit of the superconformal index matches for all values of n. Okay, so this is sort of something which I can sum up in sort of one quick statement. So we constructed the non-Lagrangian n equals 1 gauge theory, constructed by gauging together a bunch of strongly coupled n equals 2 SCFTs, and using the techniques that we know to understand for the n equals 2 SCFTs, combining them with the n equals 1 gauging, we could see that this theory flows to a point on the conformal manifold of n equals 4 Young Mills. We verified this duality by matching a bunch of anomalies, by checking the chiral operator spectrum, and by computing the superconformal index and comparing them and seeing you get the same answer. So you start with an n equals 1 theory, and what you find is that when you flow into the infrared, supersymmetry gets enhanced sort of maximally up to n equals 4. And it's also a nice bonus that the n equals 4 theory is Lagrangian. So not only do you start with some strongly coupled thing, you get supersymmetry enhancement and a Lagrangian description after gauging. So this sort of raises an interesting question that we hope to look at a little in the future. We have a lot of powerful techniques for studying maximally supersymmetric Lagrangian theories. Can we use some of these techniques now to feed back in and learn something about the Argyres-Douglas SCFTs, which we used as building blocks in this construction? Yes. Okay. And then there is this point. There is this point that I sort of made earlier. What about the supergravity duals to these theories? So these must experience this kind of remarkable cancellation between the closed string modes. Let's assume for the moment that they don't have brains. It's not important, but it makes it easier for me to say. There must be some cancellation between all of the Kaluza-Klein modes that come when you reduce the 10D supergravity on EX5 times some internal space, such that all of these things cancel out. So why should that happen? Well, when you see this kind of remarkable cancellation occurring, what you should think is there some symmetry? Is there some symmetry which protects this quantity from corrections? And of course, in n equals 4, we know there is such a symmetry. It's just the n equals 4 supersymmetry itself. But this seems to be something which persists in this class of theories that you construct by gauging things. And we would like to understand what this is a little bit. Okay, so another point I want to make is that these theories have a whole bunch of relevant operators. And we saw that, I wrote that in the superconformal index from, you can just read off that there's a whole bunch of relevant operators and various representations. So these things, possibly they trigger superpotential deformations that give you flows to new interacting SCFTs. Do these SCFTs also have these kind of interesting behaviors related to n equals 4 Young Mills? Do they flow to n equals 4 Young Mills, like the example that I gave you, the duality I gave you a few minutes ago? And perhaps inside of this space of things, there are new supersymmetry enhancing infrared dualities between strongly coupled theories and some other interesting things. N equals 4, n equals 3, something SUSY enhancing. So new dualities are always exciting, so that would be fun to explore. And in fact, we're writing a paper now about sort of all of these possible superpotential deformations and what might happen here. And so I leave you just with this little picture of sort of, there's a lot of intricate structure to these deformations. And this is just one simple example, which is the example I showed you where you actually add 2 adjoints and you just have one of these n equals 2 SCFTs. So yeah, I think there's a lot of fun questions, a lot of mysterious behavior that I think needs some explaining, and hopefully all of that will happen in the near future. So thank you for the invitation to come to this workshop, and yeah.
Thank you very much for the line up.
Do you have evidence for whether the theory is for
So yes, so you land on the point of the n equals 4 conformal manifold, which preserves U1 squared flavor symmetry. So like the beta deformation. Yeah. Right, you don't actually land precisely on the point that has n equals 4 supersymmetry. So you land somewhere on the n equals 1 preserving conformal manifold of n equals 4. And that's the point which lies on the beta deformation. Or the sum of this.
I think I'm in some ways reiterating Sakura's question.
Mhm.
But is there any hint of SFT?
Yeah, it would be nice to see you say you want to see, you know, so okay. Yes. So when you do the index computation, you see that there are a bunch of relevant marginal operators. And then you say, okay, I look at my marginal operators and I would expect to see some kind of SL2Z behavior moving these things around. I think it's a little more subtle because of some of the reasons sort of discussed in like Lee and Strassler. So you could say the same thing about n equals 4. You look at the relevant operator spectrum, marginal operator spectrum, you see 3 marginal operators plus the gauge coupling. But then the gauge coupling is broken by an anomaly from the gauge group itself. So it's a little subtle to know how to see the SL2Z across the conformal manifold like that. I think it would be nice to do that, but I'm not sure how to do that, just thinking from like a conformal manifold perspective.
So you have a geometric interpretation of the gauge. So for example, in the case of some Remarkably, some calculations, Sally showed that in some cases you can see that it go back and then you see the same side of power. Can you see anything like that happening here with these examples?
So in this last slide that I showed you here, if I can go back. So essentially, one of the things which happens is that if you start with a theory which has A equals C and you do a superpotential deformation, you obtain another theory with A equals C. So now you can ask, where do these things flow to? And there we go. It turns out a lot of them flow not in a conformal way, but like, you know, a proper relevant deformation RG flow to something like n equals 4. So you could perhaps explain this by saying that these are theories which are sort of continuously connected by a certain class of deformations that I don't quite understand. Like obviously there are deformations that go to n equals 4 which don't start with A equals C and vice versa. But the structure seems to be to do with study the space of RG flows with some adjectives that I don't necessarily know fully. And that takes you to something like n equals 4. Or maybe it's a theory with 2 chiral multiplets or something, which also sits on the same conformal manifold. Yeah, but I think one of the things that would be nice is to have some kind of top-down understanding of, instead of thinking of this as gauging a bunch of 4D n equals 2 theories, I should say, well, is there a geometric construction of this theory a priori? Well, I mean, these things, okay, so you could look at like the Labial hypersurface interpretation and type 2B and then try and introduce you could play this game, but I'm not super satisfied everything is under control playing that game from the geometric perspective.
One there's different from top down. So one would be a little but then it is one using like any top-down construction of figures that complaining about.
Yeah, so let me just, in case it was too quiet, Mike. so there is some examples where these gaugings actually, you know, they don't look like they're in class S because you gauge a whole bunch of different things together, and that's not a pair of pants decomposition of a Riemann surface. But there are cases where there are class S descriptions which are product theories. And then if you gauge 2 of these together, it's like you're gauging 4 theories together. And we had this paper with these authors plus Matteo Sacchi last year, where we studied exactly these things. And this gives you more of a sort of top-down understanding, like a geometric understanding that doesn't go via gauging. But also it relies on this slightly non-generic construction of having class S descriptions, which are products, which you can only build sometimes. Thank you.
Any more questions?
Then I think speaker.